Thank you very much, and this is okay. Okay. Thank you very much for inviting me to be part of this program. And I will talk about specific interfaces between, not in general, but specific interfaces between water and semiconductors, motivated by one specific problem. And when I was preparing this talk, I talked to Christian, and Christian said, keep it, give a general introduction, and also, make it very general. And so there will be a lot of things probably that, looking at the audience, I know many people here, many of you will be very familiar with. But, there will be some pedagogical introduction, and I hope you don't mind. Anyway, the motivation for us, in the last 10 years to study interfaces between water and semiconductor and insulator was to try to understand how to predict the property of materials to trigger desired photoreaction to generate clean fuel from water. And the problem, as I always say, is very simple, simply stated. You absorb light in a semiconductor or insulator. You generate electron-hole pairs. You have a way to transporting them to the interface, and you want to use these electron-hole pairs to make a chemical reaction to generate fuel. Usually this never works just with a material that is a good photoabsorber. You also need a catalyst. Of course, in practice, the problem is very difficult. Actually, we don't yet know as of today is really how these reactions work. But there has been progress in the community to understand materials and this process. And if you want to understand this process, a prerequisite is to have a microscopic structural model of interfaces, and of course to understand the interaction between light and matter, and to be able to do computational spectroscopy in a way. So I will spend quite some time to tell you about the method that we have used or have been involved in developing to investigate interfaces, especially electronic structure method. And then I will give you an example on a specific interface to show you what we have learned by applying all these methods. And because this is an IPAM workshop, I will spend more time on the first part and a little bit less time, although of course I will present results on the results that are more material science specific. Okay, so what do we do? When we want to study an interface from first principle, first question is, what is the structural model? And we derive a structural model from first principle molecular dynamics and using density functional theory. And these days, we have started, as many in the community, also to use forces and energy from density functional theory to generate machine learning interatomic potential, although by no means we are expert on that, and we have done actually very little in that respect. So let me tell you what the challenges are from the very first, from the beginning. First of all, if you have system with very dissimilar, dielectric and electronic properties, finding a density functional that is appropriate for both the system is very complicated. Silicon has a dielectric constant epsilon infinity of 12, 13, water of 2, and this is a problem, for example. Then if you want to generate machine learning potential, how do you validate them over a long time scale, the time scale that you cannot simulate with density functional theory? And one problem that, in my opinion, is an outstanding open problem is how to describe different charge state and oxidation states. So the system reacts, the system changes the reaction, the oxidation states change. How do you describe them? With an interatomic potential, we have experience ourselves this kind of problems that we have not solved for systems much simpler than an interface, a defect in semiconductor. And I've seen in the literature some tendency of saying, oh, it will work out in a statistical way. And people kind of forget sometimes that electrons are really complicated and there are transition states and stuff like that. We need to focus on how to describe this system in a good way. Okay, so once you have your structural model, you want to probe the system, right? How do you know that you're right? And you want to do spectroscopy. And you can do optical spectroscopy, and here I just mentioned some that we are able to deal with from first principle, some we are not yet able to deal really well, and then also vibrational spectroscopy. Of course, you want to do optical spectroscopy because you want to probe your system and compare to experiment to understand whether your structure is right, but also because you want to study light-matter interaction, right? Because that's the problem that I told you about at the beginning. And over the years, we have developed algorithms and also method to do many-body perturbation theory, time-dependent DFT with forces, and also quantum defect embedding theory to study a number of electronic structure calculations that are useful for interfaces, and I will tell you about those in a minute. I want to point out that there is not one single calculation or electronic structure that will do a job for you, whatever interface you're studying. You need to compute many different electronic properties. You need refinement procedures to validate your structural model and to understand light-matter interaction. Okay, so here the challenges, first of all, are the same as with the structural model right away, the level of theory. Even if you only do a time-dependent density functional theory for absorption, the question that you're facing right away is which functional, right? And if you have different, which you always have in an interface system with different electric property, it's an issue. One really important and difficult issue is how do we carry out complex electronic structure calculation for a system that we have generated with machine learning. So, and again, I will tell you about an example of a system where we were able to do a very large system by fitting to a machine learning potential. And then we faced the problem, we cannot do electronic structure calculation for the whole system. How do we reduce the size so that we are able to do that? And the other question that we have been asking many times, how can we fully understand the experimental setup and the samples used experimentally for comparison? And, this is a very, very, so, do you really need, what is the level of details that you need? This is a very, very difficult question. And by the way, please interrupt me anytime, and I'd be happy to answer questions during the talk. Okay, so one thing that we all know, but we don't have to, it's better not to forget it, is that whatever you do, when you say we do calculation beyond DFT, we do calculation at a very high level of theory, all calculation that you do have DFT as input, okay? I don't know any, certainly ours, but I don't know any calculation done at a very high level for realistic system. There are quantum chemistry calculations, of course, that are not done with DFT as input, and they are multi-reference from the start. But calculation for the system that I will present, I don't know any that doesn't have DFT as input. So you cannot solve this problem with DFT only, but certainly you cannot solve this problem without DFT. And so which functional? I will present results obtained over, over many years. And at the beginning, we were looking at interfaces between water and semiconductor simply using PBE. This is a semi-local functional, very popular in condensed matter physics. And in the last few years, we have done simulation almost exclusively to get the structure based on SCAN. This is a functional derived 10 years ago, proposed 10 years ago by John Perdue and others. The references are here. And basically the choice of SCAN, the motivation is to have a decent representation of water. This is and it also does a decent job for all the structural property, not electronic, but structural property of the oxides and semiconductors that we have studied. But really that was the motivation. SCAN is not enough in terms of even qualitatively reproducing trends. So if you want electronic properties, you need to do something different. And in many cases, we do hybrid functional calculation on SCAN trajectories or hybrid functional and many-body perturbation theory on SCAN trajectories. And let me tell you about just a development about hybrid functional that we have come up with recently. You know, zillions of people have worked on hybrid functional. I'll telling you about my work, but of course there is a lot of work out there. So this is the exchange potential that enters the Kohn-Cham equation that we split in long range and short range. And one thing that we started using 10 years ago is as a mixing fraction between local and Hartree-Fock. And if you are not familiar with the words I say, I can explain them. As a mixing fraction, we use the inverse of the dielectric constant. And actually for solids, and for many solids non-metallic, as you can imagine, it does a decent job for band gaps, for example. And you can have a range separated version that also that has been developed by us and also further developed by the group of Alfredo Pasquarello. And you can get decent results. However, as you can imagine, epsilon infinity is for one solid, right? When you have multiple solids joined together, what do you do? And of course, you can do HSC or stuff like that, which we have done. And recently, we have generalized this functional by introducing a dielectric, a local dielectric. It's not a constant because it depends on field. It depends on R. That is a generalization of this functional here. So these are the paper where we. These are the paper where we. I'm not doing well here. Okay. Okay. I am not getting it right. Okay. So these are the paper where we did this generalization, and I warn you. Up to a certain point in the paper, the generalization is very well theoretically justified, but to get to that expression, the last step is not well theoretically justified. And we made this approximation because we wanted something that was separable when you do the calculation. And this is computed with maximally localized wave function and so on and so forth. We can discuss that. And we have used it for several interfaces and also for band gap of oxides. And this generalization, also for reason that I must admit we don't fully understand, works pretty well for band offsets, for what we know, and also for band gaps, also of complicated oxide, like the spinel structure of cobalt oxide. Okay, so starting from DFT, we have developed many-body perturbation theory methods, GW, BSC, as I said, time-dependent DFT and QDET, that we have optimized also to run on GPUs, and they are listed here. And I will briefly tell you what they are and how we use them for interfaces. and they are implemented in this code called WEST. So GW, that is a method to compute quasi-particle energies. We started working on this about 10 years ago, and the GPU accelerated version is more recent. In the context of interfaces, is used to compute band offsets, okay? And I'm sure that most of you know that, but for those who don't, what we solve is the head-in equation. So instead of the exchange correlation potential, as we have in density functional theory, we have a self-energy, which is given by a Green's function multiplied by a screened Coulomb interaction. And in this screened Coulomb interaction, there is a dielectric matrix to compute, and our contribution has been to understand how to compute this dielectric matrix a long time ago by doing a spectral decomposition so that we don't have ever to compute explicitly empty states. You can then use the same techniques to solve the Bethe-Salpeter equation to get a neutral excitation. And what we have now is the ability to solve Bethe-Salpeter starting from GW on top of hybrid functionals. And I would like to bring your attention to the fact that here, and this is very recent work published last year, we can do Bethe-Salpeter calculation for system with about 2,000 atoms. And finally, we can converge calculation for vertical excitation energies and also for absorption spectra. And this is a system which is pretty complicated. It's a system with dislocation. And again, for those of you who are not familiar, our way of solving the Bethe-Salpeter equation built on work done almost 20 years ago in the group of Stefano Baroni for time-dependent density functional theory. I'm not going to explain everything here, but I just want to tell you that we start from a quantum Liouville equation where there is a self-energy, same self-energy of 2 slides ago for GW, and depending on how you approximate your self-energy, you can write down the equation of time-dependent density functional theory or the Bethe-Salpeter equation. And these were written down by Walker et al., and we generalized this to the Bethe-Salpeter equation. Because we can do this very fast, because we don't compute empty states, and there are also a number of other things that we did that we can now do calculation for 2,000 atoms. Recently, we were able to generalize time-dependent DFT, spin flip, so we can do different spin states, and compute forces. This is very important because we can compute forces in the excited states, and in addition to absorption, we can do emission. We can do photoluminescence that we have not been able to do for a long time on systems that are, again, pretty decent, 1,000 atoms. Okay, so all of these theories are pretty old. GW, 1965. Time-dependent DFT, 1984. Hardy Gross and Walter Kohn. And what our contribution has been algorithmic contribution to understand how to do the calculation in a different way. Recently, we have developed, I'm not sure I would call it a theory, but a framework also to compute multi-reference states. Let me try to explain in general what we want to do. We have a system that has a region with localized states, and these states are not representable by mean field theory. We want to use quantum chemistry method like configuration interaction to understand these states, and by setting up an effective Hamiltonian written there in second quantization. And we want to put the effect of the environment into this Hamiltonian so that we have these states embedded in the environment. So for an interface, this is very difficult to do. We have been successful so far for defects in semiconductors. And for an interface, we have done many attempts, but this is more difficult, meaning that you have to identify your region where the states are localized and during the chemical reaction remain localized, which in several instances doesn't happen because states localize, delocalize, and relocalize, while in a defect in semiconductor it's easier. But if you identify this and then you identify the region on your surface, this, by the way, is the silicon carbide surface, where there is your region of interest, you can embed it. We have done calculation with this framework that we call quantum defect embedding without empty state again. And because we can use the input of GW and the input of all the development that we have done over the year, we have now a scalable framework to, again, solids with hundreds of atoms, and we can do multi-reference state. We can do configuration interaction or something, CCSDT or whatever, depending on how many states you have embedded in a solid. Again, warning, the goal is to apply this to interfaces. The successful results for now are for defects in solids, and for interfaces, we have very little. Okay, so this is all the machinery that we use in different ways. I will point out here and there when I present results what we do to do computational spectroscopy. And the other very important spectroscopy, if you want to look at interfaces, is vibrational spectroscopy. This is spectroscopy. Many people have worked on this, and we worked on ways of using correlation function of the polarizability and the dipole moment for IR spectra. We started a long, long time ago, 15 years ago, and also to do some frequency generation. If you do a polarizability dipole moment correlation function, once more, many people worked on this spectroscopy. And recently, we have done first principle molecular dynamics simulation in the presence of an electric field, and we have computed Raman spectra to identify what happens at the interface, and ask the question, depending on the sign of the field, how is the structure of water modified at the interface, and are there Raman signatures? And it turns out that there are Raman signatures, and these are explained in these two papers. So the challenges certainly are the simulation timescales, especially for some frequency generation. Also, it is surface sensitive if the quadruple contribution vanishes. And to have a quadruple contribution vanishing when you do simulation is very, very, very complicated. The other thing that I want to mention is that all these proportionality that I write here and all these prefactors that we are using are kind of made up, in the sense that this was pointed out in this paper 20 years ago, and we have all happily forgotten that this classical prefactor, when we go from a quantum, a quantum mechanical correlation function to a classical correlation function, are approximate. And I don't have much more to say about this because we didn't find out a solution, but we need to keep this in mind. And this is some recent work done with machine learning potential. This is work that basically is the same work that has been done by the group of Selloni on titanium dioxide, indeed done with her former student, Marcos Calegari. But for the bismuth vanadate surface, stoichiometric bismuth vanadate surface, and here by fitting results, first principle data, actually done with maze and deriving a machine learning potential, we could simulate very long time. I mean, for classical people, this is not long, but for me, it's incredibly long. And we could finally, we couldn't do this for a long time, have some frequency generation spectrum that start resembling experiment, but this work is not finished. I'm just telling you that finally we can do this. Last thing that I want to say, and this is something that we are incredibly excited about, is another way of probing interfaces, and this is to do quantum sensing. So let me try to explain the idea, and then I will explain what this correlation function is. So the idea is the following. You have a surface. The surface needs to be a semiconductor or an insulator. And ideally, it should be a diamond or a silicon carbide surface. It's not yet that in our simulation. And then close to the surface, you have a spin defect. And this spin defect, you want it to act as a quantum sensor. What do I mean by that? What I mean is that this spin defect can be prepared as a two-level system in a certain state. And if you measure a coherence time, how long it stays there, this T2 over there, and if your coherence time is sensitive to the proton at the interface and to the molecule at the interface, you can do nano NMR. And you have a probe that is, in principle, if the sensitivity is good, better than anything else, in the sense that to really probe the structure of the interface experimentally is incredibly difficult. So how do you, so first of all, there are data that are coming out from experiment. They are not exactly, I mean, this is difficult also experimentally. But one way to understand this is to try to understand what is the main reason for this spin to decohere. And there are reasons to approximate this by a Hamiltonian that is mostly determined by the hyperfine constant. And then if you compute in a region the hyperfine constant, and you compute correlation function of this hyperfine constant, you can get a coherence time. Of course, this is a long story. We could do this because we have also worked for many years on quantum sensor in solids. But anyway, this is what it is. This is this correlation function. These are the hyperfine tensor. There is a small problem. And the problem is that to converge this correlation function, you need several nanoseconds, and you need about 15,000 molecules. So we did this for a model system. Water is classical water with the interatomic potential. I mean, I don't exclude to do this with machine learning potential, but we are very far from doing that. But the reason why we are excited about this is that this coherence time can be connected. I mean, first of all, it's sensitive to temperature, it's sensitive to density. And also, the other thing that we are very excited about is that it is changing and it is sensitive within error bars to the presence of interfacial ions. So by measuring this T2, you could tell experimentally which kind of ions you have present at the interface. Of course, the Hamiltonian is still approximate. There are a lot of problems to be solved, but of course, it begs the question, can we track chemical reaction at interfaces by using quantum sensors? And if you can sense ions, because the T2 is sensitive to the solvation shell, you may be able also to sense whether there is an hydronium or hydroxide, and you may be able to understand whether a chemical reaction happens. We haven't done this yet, but this is what we want to do. Okay, so now, finally, I am going to...
Yeah, Giulia?
Yes.
How do you calculate the hyperfine tensor from...
Yes. Very good question, sorry. So the hyperfine tensor is computed from DFT. From perturbation theory, this is the module of quantum expression. There are a number of problems. First problem is you need to have a assumption or finite size scaling of how far from the spin defects you need to compute your hyperfine, okay? Because so you need to do a finite size scaling because you need to understand how it decays and in your solid and because there is an interaction between the electron and all the nuclei. There is a problem with pseudopotentials. We can discuss about that because of the contact of the wave function at the nucleus. It's approximate, but if you do it for something like carbon, there are so many experiments that you can understand whether the trend is correct or not. But it's not a simple deal. I mean, the calculation is very simple. There is a code, you compute it, but like, you know,
just a simpler, excuse me, question. So exactly what it is, this spin defect? Is a magnetic impurity?
For example, NV center in diamond. So this is yeah, it can...
It's not necessarily magnetic.
No, it can be. For example, if you, of all the... It is not necessarily magnetic. You have, for example, a vacancy and a nitrogen negatively charged, and there is one state of the electron that forms a spin defect. There are many magnetic impurities that people use. Molecular color centers are all magnetic, and they are more difficult for us because there is chromium, for example, and this... all sorts of things. By the way, this is, again, super approximate. This is, we could not do diamond because the diamond surface or whatever you do, it needs to be terminated. And we cannot do a system which is that big. So we took a layer of graphene, which has not a gap, but classically you can compute the hyperfine, which is not very different from diamond, and we modeled that. But it is still far from reality. But I don't know. I find this very cool, but but it's still far from reality. Okay, let's be much further from reality than anything. But you know, we started doing this 2 years ago, and all the rest we started doing forever. So. Okay, so other questions? Okay, how much time do I have?
15 minutes.
15? Okay, good. So now let's see how we solve some problems here. We want to put together an insulator and water, and so we need to understand, are the absorption spectra good or not? And for this, usually when we start looking at the oxide, we do many-body perturbation theory with the Bethe-Salpeter equation. And for water, especially if there are ions, you need to use hybrid functional. Then it's all a matter of understanding, not all, but it's very important to understand band offsets, to understand whether the charges go where you want them to go. And so here we do first principle and decoupled with all the spectroscopy that I spent a lot of time telling you about. And in some cases, we have done also coupled our calculation with some Marcus theory investigation to understand some charge transport. So I will go very quickly on the results. We have studied the bismuth vanadate. It has been studied theoretically by many people, including Alfredo Pasquarello. And I want to acknowledge also the work of Giulia Victor, who, by the way, pointed out to us that we had forgotten a charge state of a vacancy in bismuth vanadate, and very gently and very nicely, and I would like to acknowledge her work here. So all the calculation that we have done on bismuth vanadate water have been done over many years with my experimental collaborator, Kyung-Shin Choi from UW-Madison. And these are really integrated work theory and experiment. And I'm telling you, quickly now what we have done and understood. First of all, oxide substrates are defective, and you need to understand the role of oxygen vacancies. This is very important. And then your photoanode, if you want to use your oxide as a photoanode, usually is n-doped, and you need to understand also the role of excess electrons at the surface. It took a long, long time for us to understand that, but finally there were experiments done at DAISY and we in Germany, and we started collaborating with several experimentalists that were showing that for this specific surface, the surface is always slightly charged. And so we took this into account. And then we did study of morphology and surface composition, going back and forth and computing many different kinds of spectroscopy, imaging, and so on and so forth. And we identify a promising realistic surface exposed to water, and which is bismuth terminated. And we could explain some results, and we could compute the band offsets. And also, the boxes there, the thickness of the boxes are due to all the fluctuation of the energy levels in our simulation. For some reason that I don't understand, we could derive a decent machine learning force field for the stoichiometric bismuth vanadate surface, but for the bismuth vanadate surface, we could not, in the sense that at some point after you use the potential that we derive for the bismuth terminated surface, the simulation breaks and starts giving junk. And we don't understand this yet, but maybe this is an interesting problem, and we will learn something about this. Once you understand that you have good band offset, you need to look at charge transport. Charge transport occurs via polarons, and we started looking at these and the polaron hopping activation energy in a very, very modeled way 10 years ago. And then more recently, we did a lot of calculation with constrained DFT with hybrid functionals. And we understood that actually the hopping of the polarons is better in the bulk than at the surface. And when the charges get close to the surface, also because it's kind of a little bit charged, they slow down, which is not what you want, but they still do that. And there is this, but it's important to understand, and this is where it's important to have the charge state of the vacancy that change as you approach the surface described correctly. There are a number of challenges. The charge transfer rates that we can have are qualitative at most. And we didn't take into account any non-adiabatic processes that for sure will be important, and they are not there. Once you have your surface, I told you, the process doesn't happen if you don't put a catalyst. And one of the catalysts that we have used is iron oxygen hydroxide. And we have found, not surprisingly, that actually the ratio of the metals at the surface affects the hydration of the surface, and then it affects the bonding of this catalyst, and then it affects the performance. And the reason why we understood this is also because in the past we did calculation to identify active sites on another similar catalyst, nickel iron oxygen hydroxide. And this really, the understanding of all these differences in solvation came from our experimentalist friends who found differences in experiment when they prepare differently their photoanode. And we spent a lot of time trying to answer why, and we changed several composition of the surface, and then we could relate the hydration of specific sites. And you know, this sentence here is a calculation of a lot of band offsets on a lot of molecular dynamics trajectories run for different composition of the catalyst. Okay, so the last thing, this is a very material science kind of stuff, and maybe not so much of interest to this audience, but I want to mention this for one reason, which will be clear in a minute. So not only you need a catalyst, but experimentally, bismuth vanadate is not stable at a lot of pH conditions that are of interest. So you need to put a protective layer. The protective layer almost uniformly used is titanium oxide. And again, experimentally, they observed that depending on how you form your protective layer, you have very different performance here, whether you put an oxygen source first or a titanium source first. And we try to understand why. And here we use the deep MD potential that were derived by the group of Celloni for amorphous titanium oxide. And the potentials are great in the sense that we could reproduce a lot of amorphous titanium dioxide properties. It's all beautiful, except that when you put your titanium dioxide that you have generated with the potential with, I don't remember how many atoms, 2,000 or 3,000 on bismuth vanadate, you cannot do electronic structure calculation because it's too big. So we spent a lot of time trying to generate generate this the way. By the way, the structure was also online. Generate with deep MD and then reducing the sample and to keep the major motifs that you would find in the big sample. But anyway, let me cut a long story short. What we found is that if you do a certain deposition, you leave water at the interface, just few water molecules. And when you leave these few water molecules experimentally and you have a wet layer, all band offset and solvation properties change, and then also the performance changes. Again, this is the result of a lot of calculation and molecular dynamics, but we could explain the results that this is a paper that we have just published that were obtained experimentally. So we learned about what it's in a way obvious but important to keep in mind, especially in certain communities, that interfaces are a dynamical system. The electronic property at finite temperature and dynamical fluctuation are key, are critical. You cannot solve any of those problems without taking them into account. And the other thing is that really, when we talk about experimental validation, don't forget the S. It's experimental validations, because you need to go through a number of comparison and refinement with experiment. Okay, so let me conclude by telling you summarizing some open question. So the level of theory used to describe interfaces needs, of course, improvement. I told you what we have done. Not specifically, but We use either many-body perturbation theory or hybrid functional. I didn't talk about metals because we are not able to do metals with all the methods that I described very well or not at all. So this is a problem. Already mentioned, we are stuck at orders of magnitude in the best case scenario with the rates of charge transfer. How do we split water? We have not solved the problem. Don't take it negatively. I mean, we have learned also as a community huge amount of things about the materials, how things work. But if you ask me what happens in a 4-electron reaction, exactly how water is split, we don't yet know. We don't even know the 2-electron reaction for the H2O2 production. But there is progress. There is progress in simulation of forces with in the excited states, and maybe we will be able to get there. I want to mention, this I mentioned many times, how do we carry out electronic structure calculation on big samples generated by machine learning? And this is more for maybe another audience, but it's a plea to experimentalists, right? We need to understand what they have in their samples and what is it that they have. And so we need foundries where they tell us how they make the samples and how they prepare the samples and how it is characterized. And there is a quantum foundry for systems that are much simpler than interfaces at Argonne, where people are trying to do that. In terms of validation of data, robust data for interfaces are very scarce, and this is certainly a problem. And of course, we just don't need only to generate more data, but a lot of development are required to make progress in this field. So I list here the people I talked about. DFT, this is my student who worked at this. Postdoc, now at Flatiron, but who worked on excited states are here. And I mentioned work that started 10 years ago when Yuan Ping was my student, and she's now a professor at W. Madison. When he was my postdoc, a few years later, now professor at UT Austin. Giacomo Melani, now any researcher, and these are more recent students and postdoc. My work is funded by DOE and NSF. I don't know for how long by NSF, but as of today, it's still funded by NSF. And Computer Time, NERSC, and Chicago. Thank you very much.